require a lot of time, but rational functions. They are extensively discussed again in Calc 1. Now, I'm only looking at three types, type 1, type 2, type 3. Don't get upset, nobody calls them type 1, type 2, and type 3. Okay, I do. Because it's easier to identify. Are there more than 3 types? Yes, there are. But we cannot address them in this class. That's all we can look at. Type 1, 2, and 3. What do I mean by this? And let me give you a few examples. So f of x equals x plus 1 over x minus 2. Or f of x equals x squared minus 1 over 2x squared plus 2x minus 1. These are category 1, type 1. Here's another one. 1 over x. Or f of x equals x minus 1 over x squared minus 4x plus 4. These are both type 2. Final type, type 3. X cubed minus 1 over x squared minus 2. And you can say you're just throwing some rational functions at us. What are these? I mean, how do you even put them in these categories? And here is the answer to that. See, this category has same degree over same degree. Degree 1 over degree 1, degree 2 over degree 2. So this is category 1. Very clear. Very easy. Category 2 is also very easy. The degree in the denominator is bigger than the degree in the numerator. Degree 0, degree 1. Degree 1, degree 2. So, smaller over bigger. Same over same, same degree over same degree. Bigger in the denominator, bigger in the denominator, bigger degree in the denominator. This is the most cumbersome of the 3. Why? Because the degree of the top is by 1, exactly 1 degree larger than the denominator. So, let me summarize. Degree 1, type 1, degree n over degree n. Type 1, nice. Type 2, degree n, degree n greater than n. Bigger in the denominator, not even equal. No, these are equal. Degree n, and this is bigger than degree n. And the last one, at the top, degree n plus 1. Degree 5, degree 4, degree 7, degree 6, degree 3, degree 2, degree 2, degree 1. And this is the most cumbersome to work with. Okay, what are the differences? These two, number 1 and 2, have horizontal asymptotes or asymptote. Number 3 does not have a horizontal asymptote. No horizontal asymptote, but slant asymptote. In case you're wondering why is she talking about long division and synthetic division, yada yada yada, for this. To be able to find the slant asymptote for category or type 3. Okay, we're going to look at examples in a moment. What is a horizontal asymptote? What is a slant asymptote? And do we remember there is a third type of asymptote? What are these asymptotes? So vertical, horizontal, slant. 3 different types. A vertical, we've seen it with domain and everything. So here's a vertical asymptote. A vertical line where the function is undefined. This is the vertical asymptote. I'm going to put a number in there, x equals 4. It's a vertical asymptote because the function goes to infinity, negative infinity. There are 3 options. I would say 4. Both sides positive, both sides negative, and so this is a vertical asymptote. What is a horizontal asymptote? Here's a horizontal asymptote. I'm going to say y equals 2, where the function does this, for example. It's a horizontal asymptote, and we are talking about end behavior. Here we are talking about the behavior near this number, x equals 4. Here we're talking about behavior at infinities. The function approaches 2 as x goes to infinity. As x goes to negative infinity, the function approaches 2. So this is a horizontal asymptote. Slant, as I promised, is the most cumbersome. Here is the slant situation. Something like this. Let's say y equals x plus 2, for example. What will the function do? Okay, the function will do this. Still approaching. That's why it's an asymptote. The function approaches the asymptote, approaches the asymptote, approaches the asymptote, approaches the asymptote from above, below, whatever. But it has to approach it eventually. So as x goes to infinity, the function values go to infinity. As x goes to negative infinity, the function values go to negative infinity. So when we say asymptote, the function better approach it. If it doesn't approach it, it is not an asymptote. So coming back to the most cumbersome one, this one does not have a horizontal, but it has a slant. All 3 types can have vertical. So 1, 2, and 3, all of them can have vertical. Only type 1 and type 2 can have horizontal, and only type 3 can have slant. But of course, the ones with the slant, they can also have vertical. And now let's look at, this is a lot of theory here. It's a summary of a lot. And let's analyze and graph some functions. Allow me to choose the first one, and then you'll choose the next. Okay, so I'm going to try to choose an example from type 1 and type 2 and type 3. Any questions? So again, what are the asymptotes? Some lines that show some behavior of the function. What is the behavior here? Either negative infinity on both sides, or positive infinity on both sides, or positive negative, or negative positive. It shows the behavior of the function where it's undefined. What about here? This asymptote shows the behavior at infinity. What does the function do as x goes to infinity or x goes to negative infinity? Again, what does this say? It says that the function, the behavior of the function is when x goes to infinity, y also goes to infinity. as x goes to negative infinity, y also goes to negative infinity. Different type of behavior. Okay, so let's start with, I'm going to start with a simple example. I don't see on the handout a simple example that I would like to start with. Okay, so I'm just going to make one up, or the one that we had, it doesn't matter. I'm on page 7. So we would like to look at type 1 first. Type 1 will be just a simple example like x plus 1 over x minus 2. The question here is graph. Analyze, graph, everything, present everything you can, symmetry, everything that you can about this function. I will never start graphing a function or even analyzing it or looking at it before I identify the domain. Can anyone tell us what is the domain of this function? That is the absolute first step when I'm asked to graph. Anyone, please? Anyone? Can anyone tell us the domain of this function? Is anyone with me?
Is it possibly a real number at step 2?
Excellent. Who was that? Excellent, thank you. Yes. So 0 has to be in the table, 2 has to be in the table, and everything except 2. Everything except 2 means this. There is nothing I can write under 2. Knowing that, I will immediately state that x equals 2 is a vertical asymptote. It must be. It must be this situation. Not at 4, but at 2. It must have a vertical asymptote. It's a rational function. It is of type 1, the same degree over same degree, and it must have x equals 2 vertical asymptote. Once I say this, I will immediately write this. However, I don't know the sign, so I cannot jump into conclusions just yet. I know they have to be infinities, but I need to know both positive, both negative, negative positive, or positive negative. For that, it's very easy to imagine that I plug in, and I will not put it in the table, I will not use it for any other reason, but I'm imagining that I plug in 1.9, and I imagine that I plug in 2.1. Very, very close to 2. 1.9 is close enough, 2.1 is close enough. So can anyone just tell us the sign? No calculations. When you plug in 1.9 here and here, I just want the sign of the answer. Not the answer, just the sign. And when you plug in 2.1 and 2.1, what sign do we get when we plug in 1.9?
Negative.
Of course, because it's positive over negative, there is no discussion. Great job. Who was that?
Evan.
Thank you very much. Now let's plug in 2.1. Just the sign.
Positive.
Very good. Thank you so much. The other Kevin. Thank you. Great job. Good. So that is established. Now, I have to find x and y intercepts. So first I have to plug in 0 here and tell me what is the y-intercept when we plug in 0.
Negative 1/2.
That's it. Good. Next, I need to find the y-intercept. That was it. Sorry, the x-intercept. How do we find the x-intercept for any function? We know that.
Set the function equals 0.
Excellent. Thank you so much, Kevin. So the function equal to 0. When is a fraction 0? When is a fraction 0?
When x equals -1.
Yes, very good. Awesome. All right, thank you. So a fraction is 0 only when the numerator is 0. So please remember, a divided by b is 0 only if a is 0. Because we know what happens if b is 0. It's a tragedy. When x is 2, it's a tragedy, right? So indeed, when x equals -1. I put it in the table correctly in ascending order. Final step, because we know it's not symmetric, we can write f of -x does not equal f of x, and it will not equal -f of x. Plug it in and you'll see, not symmetric. Final step is this. Okay, what is that? Well, it's so-called end behavior. Very simple. For same degree over same degree is the leading coefficient over the leading coefficient, and that is also the horizontal asymptote. So the end behavior in this case is the same. In this case, type 1 is the same with y equals 1 horizontal asymptote. Leading coefficient over the leading coefficient. For all type 1, the end behavior, which is also the horizontal asymptote, is obtained by dividing the leading coefficient by the leading coefficient. 1, 1, make myself a note, y equals 1 horizontal asymptote. I'm done. This is it. I'm ready to graph. I don't care for any of the gibberish that I see here. I only care about the table. I summarized all the information in the table. That's all I need. So, I'm going to graph. When I graph a function with asymptotes, I have to graph the asymptotes first. So, y equals 1. They are not solid lines because they are not part of the graph, but they have to be graphed. They're not part of the graph of the function, but they have to be graphed first. X equals 2. They're not solid lines. They have to be graphed. They're not part of the graph. And now, slowly but surely, I graph what I see. From approaching 1, crossing at -1, 0, crossing at 0, -1/2, and going to -infinity on the left-hand side of the vertical asymptote. From approaching 1, crossing the x-axis, crossing the y-axis, approaching -infinity from the left-hand side. Okay, very simple. Please show that the function approaches. We say asymptotically. It approaches, not touches, but approaches. On the other side, it's coming from positive infinity, dropping to 1. From positive infinity, dropping asymptotically to 1, asymptotically to the vertical asymptote. And this is the simplest possible, maybe not, but a simple type 1 rational function. This is gibberish now. I don't care for any of that. I summarized all the information in the table. I go point by point from left to right. I read all this information and I graph it accordingly. From approaching 1, crossing the x-axis, crossing the y-axis, approaching negative infinity on the left-hand side of the vertical asymptote. Now I look on the other side. It's coming from positive infinity asymptotically, not here, right? Close, close, dropping towards the other asymptote, closer and closer to 1. And these are all type 1. So type 1 always has the horizontal asymptote and the end behavior obtained by the leading coefficient over the leading coefficient. Type 2 is even easier. So let's look at the type 2. And I'll explain why type 2. So I'm choosing now 12 for type 2. So r of x equals 6 over x squared minus x minus 6. So type 2, why type 2? Because the degree in the denominator is higher than the degree in the numerator. So the nice part for type 2 is this. Always and forever. Once you see a type 2 rational function, you know that the end behavior and the horizontal asymptote must be 0. That is a must.